When most people think about 3D printing, they imagine custom phone cases, plastic toys, or hobbyist projects. But one of the most demanding industries on Earth has quietly embraced this technology for a very different reason. Not because it's fashionable, because in some cases, traditional manufacturing simply reaches its limits. Today, some of the world's most advanced jet engines contain metal components that were never cast, forged, or machined in the traditional way. Instead, they were built layer by layer from metal powder with geometries that would have been impossible to manufacture just a few decades ago. But here's the real question. If additive manufacturing is such a revolutionary technology, why hasn't it replaced conventional manufacturing everywhere? Why do we still machine billions of metal parts every year? The answer is surprisingly simple. Additive manufacturing is not universally better. It becomes superior only under very specific technical and economic conditions. And almost no industry combines those conditions as perfectly as aerospace. More specifically, the heart of every aircraft, the jet engine. In this video, we'll explore why jet engines have become one of additive manufacturing's greatest success stories. We'll look beyond the technology itself and focus on the engineering and economic forces that make this partnership so powerful. Let's begin with the first reason: complexity. Not visual complexity, engineering complexity. Every stage inside a modern jet engine performs a different function: compressing air, burning fuel, extracting energy, accelerating exhaust gases. Each component operates under completely different mechanical and thermal conditions. Some turbine blades experience temperatures approaching or even exceeding the melting point of the metal itself. They survive only because of advanced superalloys, thermal barrier coatings, and sophisticated internal cooling systems. Those cooling passages are not decorative details. They're carefully engineered channels that guide cooler air through the interior of the blade, protecting the metal from catastrophic failure. Manufacturing these internal geometries using conventional machining is extraordinarily difficult. In many cases, the cutting tools simply cannot reach the required locations without compromising the design. Engineers have long understood what the ideal geometry should look like. The challenge wasn't imagination. It was manufacturing. Traditional processes imposed design constraints that often forced compromises between performance and manufacturability. Additive manufacturing changes that relationship. Instead of removing material from a solid block, engineers build the component layer by layer. Internal passages, lattice structures, and highly organic shapes become manufacturable for the first time. This doesn't mean complexity becomes free, but it changes the economics dramatically. In conventional manufacturing, every additional feature usually requires more machining, more tooling, or more assembly. In additive manufacturing, geometric complexity often increases far more slowly than manufacturing effort. And that's our first key insight. Jet engines are not an ideal application for additive manufacturing because they're expensive. They're an ideal application because the physics of flight demands geometries that conventional manufacturing struggles to produce efficiently. Complexity isn't a side effect, it's the requirement. And whenever geometry becomes the problem, additive manufacturing begins to look like the solution. But complexity alone doesn't make additive manufacturing economical. There is a second condition that matters just as much: production volume. And this is where aerospace becomes very different from industries like automotive. Imagine you need to manufacture 10 million identical components. Investing heavily in specialized tooling can make perfect economic sense. The cost of that tooling is spread across millions of parts. But now imagine producing only a few thousand components, or a few hundred. The economics change. That same tooling investment suddenly has far fewer parts over which to recover its cost. Aerospace lives much closer to this second scenario. Aircraft engines are sophisticated, expensive products, but they are not manufactured at the enormous volumes of consumer electronics or automobiles. Additive manufacturing changes the equation because the machine does not need a dedicated mold or die for every new geometry. The digital design can be modified, prepared, and sent to the production system without rebuilding an entire tooling infrastructure. This creates an important economic advantage for low-volume production. When tooling represents a large portion of total manufacturing cost, eliminating or reducing that fixed investment can make additive manufacturing much more competitive. Of course, additive manufacturing is not free. The machines are expensive, production can be slow, and post-processing can require machining, heat treatment, inspection, and other steps. So the real question isn't whether additive manufacturing is cheaper in isolation. The question is whether its total economics are better for a particular component at a particular production volume with a particular design. And that brings us to the third condition, part value. Because when you're manufacturing components from expensive materials, the economics of how you use that material become extremely important. Jet engines rely on materials such as titanium and nickel-based superalloys because they have to survive extreme temperatures, stresses, and corrosive environments. These materials enable performance, but they also come at a price. Consider a conventional machining process. You may begin with a relatively large piece of expensive material and remove everything that isn't part of the final geometry. Aerospace engineers often describe this relationship using the buy-to-fly ratio, how much material you have to buy compared with how much remains in the final flying component. The closer that ratio gets to 1, the more efficiently the material is being used. Additive manufacturing approaches the problem from the opposite direction. Instead of starting with a large block and removing material, it deposits material where the component needs it, building toward a near-net-shaped part. And now we reach one of the most important economic drivers in aerospace: weight. In an aircraft, every kilogram has consequences. A heavier aircraft requires more energy to fly, and that cost accumulates over thousands of flight cycles. This is where additive manufacturing becomes particularly interesting. Because it can produce internal structures, optimized walls, lattice geometries, and complex shapes, engineers can sometimes remove material without simply removing performance. The goal is not to make a part lighter for the sake of it. The goal is to put material where the loads actually require it, and nowhere else. There is one more advantage that may be even more important than weight reduction: part consolidation. And this is where additive manufacturing can change not just how a component is made, but how the entire component is designed. In conventional manufacturing, a complex component may be divided into multiple parts because each part has to be manufactured, inspected, and assembled using processes that are physically accessible. But every additional part creates another interface, another tolerance, another assembly operation, and potentially another location where something can wear, leak, loosen, or fail. Additive manufacturing can approach the same engineering problem differently. Instead of asking how many pieces can be manufactured efficiently, engineers can ask a more fundamental question: how many pieces actually need to exist? This is an important shift in design philosophy. The objective is no longer to reproduce an existing assembly with a 3D printer. It is to redesign the assembly around the capabilities of additive manufacturing. One of the clearest examples comes from the LEAP engine. GE redesigned its fuel nozzles specifically for additive manufacturing, transforming what had traditionally been a multi-piece assembly into a single printed component. That change matters because the benefit isn't simply fewer parts on an assembly line. It can also mean fewer interfaces, fewer assembly operations, and a component that can be designed around its actual function rather than around the limitations of joining separate pieces. And now we can see something important. Complexity, low production volume, expensive materials, weight reduction, and part consolidation are not 5 independent advantages. They reinforce each other. And the story becomes even more interesting when we move beyond individual components. GE's Catalyst turboprop engine demonstrated how additive manufacturing could become part of the architecture of an engine itself, rather than simply a replacement for one traditionally manufactured part. This is strategically important because it shows where additive manufacturing can create its greatest value, not when engineers simply substitute one manufacturing process for another, but when they redesign components around what additive manufacturing makes possible. But there is an important caveat. If additive manufacturing were automatically cheaper, faster, and better, every engine component would already be printed. That clearly isn't the case. Additive manufacturing still has significant constraints. Build rates can be slow, surface finish can require additional machining, heat treatment may be necessary, inspection can be demanding, and for flight-critical hardware, certification is a major part of the equation. So the competitive advantage isn't simply low manufacturing cost. It is the ability to create a component whose total value is greater than the cost of producing it additively. And this gives us a useful framework for thinking about additive manufacturing as an investor. Don't ask whether an industry uses 3D printing. Ask whether the economics of that industry make 3D printing valuable. A promising application is more likely to emerge when several of these conditions overlap: complex geometry, relatively low production volumes, expensive materials, high value placed on weight reduction, and opportunities to consolidate multiple parts into one. And this is exactly why jet engines are such a compelling use case. They sit remarkably close to the center of this overlap. They are complex, relatively low-volume products built from expensive materials, where weight has enormous value, and where integrating functions into fewer components can produce significant benefits. But perhaps the most important lesson is broader than aerospace. Additive manufacturing doesn't win simply because it can manufacture shapes that conventional processes cannot. It wins when those shapes have enough economic value to justify the manufacturing process. Jet engines may therefore be one of the ultimate use cases for 3D printing, not because additive manufacturing is perfect, but because the economics, engineering requirements, and design opportunities happen to align. And that alignment is what turns a manufacturing technology into a competitive advantage.